Hi, this is Dr. John Bergduff. In this video, we're going to compare different principles for counting. As you've looked in your book, you will see that we have explored three major principles for counting. The most basic of all is the fundamental counting principle, which you see on your left. The number of ways in which a sequence of successive choices can be made is found by multiplying the number of ways each individual choice can be made. Now, after we developed that, we talked about two concepts that resulted in two formulas: permutations and combinations. And those are ones that I particularly want to talk about because many students wonder, when can I use those formulas? When do I have to fall back on the fundamental counting principle? And if I do get to use one of the formulas, how do I decide which one? And then actually, how do you enter it into the calculator? So let's explore with an example. And the chart that I have here, think of it almost like a flow chart where you think your way through the question to decide whether either of the formulas are appropriate and then which one it is. So let's look at example number one. A club has 15 members. In how many different ways can you select a committee of 4 members to plan a party? Now, here's how you use this table. First of all, to be able to use either of these formulas, either one, your general scenario is that you need to be selecting R objects out of a set of N objects. Am I selecting some objects out of a set? Now, looking at this example, I believe that is true. We've got 15 members of the club, and we're selecting 4 people, 15 out of 4. Excuse me, 4 out of 15. So I think we might be on track, possibly, to use one of the formulas. But there's sort of another step we have to look at, like a checklist. Objects are chosen without repetition. No object is used more than once. Let's think about that. So if you're selecting a committee of 4 people from a group, would you select the same person twice? That wouldn't make any sense. Joe, you're on the committee, and guess what? Joe, you're on the committee. That doesn't make any sense. The objects are chosen without repetition. You would not use an object more than once. If I can make it through these first 2 checkpoints, I am definitely going to be able to use one of these 2 formulas. The question is which one? It all depends on whether you are looking at an arrangement of elements of the set or simply a subset. Or saying it a different way, is the order important or is the order not important? So if I'm creating a committee of people, I think about this. Does the order of the people matter? Does the order that I select them matter? Does the order that they sit around a table matter? Not really. If I pick the 4 people, what order I put them in doesn't matter. I'm looking at a subset of the people, not an arrangement. The order is not important. That thought process helps me realize that I can use combinations, and I can use this combination formula. The only question is who's N and who's R. R is the number of objects you select. N is the total number of objects in your set. So if we have 15 people in the club and I'm choosing 4 of them, the calculation that I am going to do will be 15C4. 15C4. Now here at the bottom, I've plugged that into the formula for combinations just so you see it. 15C4 is 15 factorial divided by 15 minus 4 factorial, that's N minus R, times 4 factorial. I'm actually going to show you how to do this 3 different ways on the calculator, just so you see. Let's not pay attention to this last one quite yet. I'll come back to it. Now, if you have a TI graphing calculator, you are in real luck because the calculator can do this entire calculation for you there's a combination button available. Here's how you use it. First of all, you have to enter that first number at the end. So you enter 15. Then you get the combination feature up, and here's how you do that. Click on Math, and if you look across these options across the top here, you'll see one that says PROB, or in older calculators, it's just PRB, and that refers to concepts that are related to probability. Use your right arrow on this little thing that looks like a wheel and wheel over and scroll over to probability. And if you look down the list, you will see an option NCR. Guess what? That's the one you want. We'll go straight down there, hit enter. You can see it's right there. Hit enter. You'll see it beginning to create itself just like the NCR formula. On the older calculators, these will sort of all be written in line. The newer versions of TI-84s, everything looks exactly the way it does when you write it. And then you enter the 4, and you hit. So it's 15C4, you hit enter, that's your answer. 1,365 done. That's it. Now, if you don't have a TI-84 calculator, it is still possible that somewhere on that calculator, there's at least a button that does tutorial. If that's the case, then you can still at least use the formula. You just have to do it through the factorials. So I'm looking over here on the left where I see how the formula is plugged in. And what I see I would need to do is I would need to take 15 factorial. Now I'm using a TI-84. Your calculator would have a factorial button somewhere. They're not all uniform. You'd have to hunt for it. But I'll show you where it is on the TI-84. And hopefully you'll find it on your own calculator. You say 15 factorial. Now the factorial is in the same place as the combination option. Click Math. Use your arrow to slide over to probability. And you'll see that right below the NCR option is simply an option that just lets you do a factorial. 15 factorial. Divided by. Now, everything in the denominator has to stay together. You're dividing by the entire denominator. So we're going to open parentheses to keep everything in the denominator in parentheses. Now, I'm going to do one part in my head. 15 minus 4 is 11. So what I'm looking at first is 11 factorial. 11, again, math, just to practice this. Slide over to probability. Slide down to factorial. Enter. There's my 11 factorial. Times 4 factorial. 4 math. Slide over to probability. Slide down to factorial. Enter. Close parentheses to close out everything in the denominator. This is not, obviously takes a little bit more work than what we are, the first way we did this, but your calculator may require it. And hit enter, and guess what? You get the same answer. Surprise. Very good. Now let's suppose that you have a really simple calculator that doesn't even have a factorial button. Well, let's go back over here on the left. What I have done right here is I've written out what 15 factorial is. We know that 15 factorial is 15 times 14 times 13 times 12 times 11, and you might wonder why I stopped. Well, on the bottom, the 15 minus 4 factorial, it is 11 factorial. I notice that I've got the 11 factorial on both the top and the bottom, which is really cool. That means that they would divide out, and I wouldn't have to worry about that anymore. The 4 factorial is 4 times 3 times 2 times 1. Basically, any calculator should be able to do this. Looking at the numerator, we would have 15 times 14 times 13 times 12. Remember, the 11 factorial divides out, so I don't need that. And I should have said I'm keeping the numerator in parentheses. Divide by, keep the denominator in parentheses. And remember, the 11 factorial is gone. So what's in the denominator would be 4 times 3 times 2 times 1. And actually, if you really had to, you could probably even do that by hand. That wouldn't be a lot of fun, but you could. 1365, guess what? Same answer. Isn't that cool? Very good. So you have like a super high-tech way to do this, a medium-tech way, and a low-tech way. And then a Neanderthal way where you just do it all by hand. I hope that one's helpful. Let's do another example or two just to explore the decision-making process and what we do on the calculator. I think it'll be helpful. In example number 2, I'm going to clear this out just so it's not distracting. How many 3-letter codes can be formed using the letter A, B, C, D, and E if repeated letters, this is not what I meant to say, are allowed? If repeated letters are allowed. Now, let's walk through this chart and see if this makes sense. Am I selecting R objects out of a set of N objects? Okay, I've got 3-letter codes chosen out of 5 letters. So yes, I'm choosing 3 out of 5. So I'm getting hopeful, getting my hopes up that I can use permutations or combinations. Objects are chosen without repetition. Second checkpoint. No object is used more than once. Uh-oh, repeated letters are allowed. As soon as you see that, you realize that you cannot use either of these formulas. You cannot have repeated objects, so neither of these formulas will do you any good. What do you do then? Well, underlying everything is this fundamental counting principle. The number of ways in which a sequence of successive choices can be made is found by multiplying the number of ways each individual choice can be made. Think about selecting this code 1 letter at a time. And each letter chosen is a choice. How many choices do you have for each letter? Okay, so for the first letter in the code, you can pick anything from out of A, B, C, D, and E. That's a total of 5 choices. Now, for the second letter, you can also choose any one of these 5 letters. So for the second element of the code, you have 5 more choices. 5 choices times 5 choices, and then guess what? For the third choice, you can still choose any one of those 5. 5 times 5 times 5. On a calculator, that is very, very simple. It's just 5 times 5 times 5. Enter 125. Oops, don't need those F's in there. Okay, so sometimes the formulas cannot be used at all. If objects can be repeated, no good, no good. Now, question 3 is actually supposed to say, what if repetition is not allowed? Now, we actually solved this problem, or some similar problems, in an earlier section. And I want to show you one way that this can be done. My cat is trying to help me here. Say hi, Samson. Hi, Samson. Okay. What if repetition is not allowed? You could use the counting principle again and think about this one position at a time. For the first number, you can pick any of the 5 choices, A, B, C, D, or E. For the second number, because you cannot repeat letters, the second letter, you only have 4 choices. You can't use whatever you picked first, so you only have 4 choices for the second one, 5 times 4. And since you can't use either the number you used for the first choice or the second choice, then you only have 3 choices left for the third position. And that tells me that I can use my formula and my calculator to say 5 times 4 times 3. Enter. 60. Only 60 if repetition is not allowed. And that's absolutely fine. I'm not using either of the formulas. I'm just thinking back to the fundamental accounting principle. But I believe one of these formulas will help us here because once again, we are selecting our objects out of a set of n. We're choosing 3 out of 5, so that's promising. And now I've added the restriction that repetition is not allowed. Objects are chosen without repetition. No object can be used more than once. That means I'm going to get to be able to use a formula. Now, which one? On the previous example, we were just looking at the set of people. We didn't care what order they were in. So we were just looking at a subset. But if I'm looking at a code out of these letters, if I put the letters in a different order, it makes a different code. The code ABC is different from the code CBA, even though both of them are using the same letters. Order is important. I'm looking at an arrangement. And word arrangement is a wonderful keyword. I'm looking at how the things are arranged. You can see that right away. So we are looking at permutations, and we are looking at 3 out of 5, so it's 5p3. How do we enter that in the calculator? Let's do it high tech, low tech, and medium tech all the way through. We won't do that every time. We'll just do this maybe one more time. On a TI graphing calculator, you can use the graphing feature, the permutation feature. Start with the 5, go to math, slide over to probability like you did for combinations, and you probably noticed this when we did the previous example. There is also an option NPR. Choose that one, and then enter the 3, and hit enter, and the answer is 60, which is just what we thought it would be. Or medium tech, you do have a factorial key, but you don't have a permutation key. The formula says that this would be 5 factorial over 5 minus 3 factorial. 5 minus 3 is 2. So I could simply say 5, then locate the factorial button. In our case, on this calculator, it's on that same probability menu. Divided by, and there's only one thing in the denominator, so you don't need parentheses this time. 2 math, roll over to probability, down to factorial, enter. 5 factorial divided by 2 factorial, enter. That gives you 60. Let's suppose your calculator can't even do that. Well, here I have on the left 5 factorial and 2 factorial written out. Notice when I look at that, these small numbers make things more obvious that both the 2 and the 1 will divide out. So really, 5 factorial over 2 factorial is nothing more than 5 times 4 times 3. Very low tech. You really could do this completely in your head almost. 5 times 4 times 3. High tech, medium tech, low tech. Guess what? The answer still comes out 60. That's awfully good. It's the same no matter how you do it. Now, if you have a TI graphing calculator that can do it the fancy way, there's no advantage really to looking at the medium tech or the low tech approach. But I wanted to show you all of those in case that's what you need. Let's look at a few more examples and just build on what we've got so far. Oops, didn't want to show that. Okay, here we go. Lotteries. So lots of people like to play the lottery and they think, oh, I know I'm going to get really, really rich. I can pick a number and maybe my number is the one that will be picked. So let's look at this situation. For a certain state, the lottery is played by choosing 6 numbers out of all the whole numbers from 1 through 54. Winning occurs if these numbers match the numbers chosen on the ball in any order. How many possible choices of tickets are there? How many different tickets could you write? Let's go through the chart as a checklist and see if one of these will fit. First of all, are we selecting R objects out of a set of N objects? We are choosing numbers from a set of numbers. We are choosing 6 out of 54 numbers. We can choose anything we want from 1 through 54, and we pick any 6 numbers. We are definitely picking 6 objects out of a set of 54. Objects are chosen without repetition. Now, the way a lottery is set up, if you think about how they have the big ceremony at the end with little ping pong balls that come up with the numbers, once a ball comes up, it can't come up a second time. There's no repetition of numbers. So you wouldn't want to pick the same number twice. If you did, there's no way you're going to win. So there's no repetition of numbers. No ping pong ball will pop up more than once. There is no repetition. That means I am definitely okay to use one of these formulas. Which one? Well, is the order important? Is the order not important? Am I looking at how the numbers are arranged, or simply what the set of numbers is? In this case, we've got it right here in the words, in any order. In any order. We don't care what order the balls pop up. On your ticket, it does not have to be in the same order as the balls popped up. The order doesn't matter. So if the order doesn't matter, we're looking at combinations. Our only question then is what's the N and what's the R? N is the number of elements in the set you're choosing from. So you're choosing the numbers out of the set from 1 through 54. That's 54 numbers. And R is the number of objects that you choose. There's 6 of them. So the solution should be 54C6. Now I think we've done some nice examples to show you how the calculation can be done medium tech or low tech. I went ahead and wrote out what the formula says this would be. So you could do this either medium tech or low tech. But I think we're good enough that we can get used to that enough that we'll just go straight to the high tech approach on our calculator, on our graphing calculator. We would say 54, and we hit math. Scroll over to probability. This sooner or later you'll do this in your sleep. NCR, and then 6. 54C6, exactly the way it looks on the formula. Hit enter. Let's put the commas in there so we see exactly what that looks like. That is actually 25 million. Sign here. 25,827,165. That's the total number of different choices that you could have for this lottery. Only one set of numbers wins. So your chance of choosing the right number is 1 out of 25,827,165. So that's why you will usually hear math professors say, don't plan to get rich on the lottery. Your probabilities are really, really low. Okay, that one question may save you the cost of your tuition for this class. I hope so. Let's look at another question. Very different setting. Let's talk through and see if we can see if one of our formulas will help here. Playing cards. How many different 13-card hands can be dealt from a standard deck of 52 cards? So standard deck has 52 cards, and if you're playing bridge, for example, you need a 13-card hand. How many ways could you be dealt that hand of cards? Well, let's go through our checklist again. Am I selecting R objects out of a set of N objects, some objects out of a larger set? I am. 13 cards I'm choosing out of a deck of 52 cards, 13 out of 52. My 13 is going to be my R and my 52 is going to be my N if everything else works. Objects are chosen without repetition. No object is used more than once. So you have to think about how that works. You're playing cards, you're dealt cards. is there any way that you could get a repeated card? Could you get the ace of spades twice? Unless you have a really weird deck of cards and you should mistrust everyone else in the room, no. There's no way you could get the same card twice. All the cards will be different. There'll be no repetition. So that means you're definitely going to be able to use one of these two formulas. It's just which one. Are you looking at an arrangement of cards or simply the set of cards that you have? Do you care about the order? Do you not care about the order? Now, there are card games where you do care about the order, but if you think about playing bridge or poker or something like that, what happens is you're going to be dealt the cards, and then you're probably going to arrange them differently in your hand, which means you really don't care about the arrangement. It's the same set of cards, whether you put, say, all the aces together and all the kings together, or if you leave them all scattered. The order is not important. It's the same set of cards. So the order is not important. You've got a subset. You've got a combination. Hope that makes sense. You don't care about what order the cards are dealt to you. You can arrange them however you pick. Order is not important. You've got 52 cards to pick from, and you're choosing 13. So we should have 52C13. Let's try that on the calculator. 52, math, over to probability, down to NCR, choose that, input the 13, 52C13 looks just the way it does right there, hit enter. Oh, wow, look at that. Now, this number needs some explanation. This is actually in scientific notation. The E in here, when you happen to see that in an answer, represents the statement times 10 raised to the following power. So this is 6.3501, et cetera, times 10 to the 11th power. That's a big, big number. Converting that to a standard number would involve sliding the decimal 11 places to the right, and that gives you the sense that this is really a huge, huge number. There are many, 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 many different hands if you're being dealt 13 cards at a time. 52C13, 6.301 times 10 to the 11 power. You may see that. Let's try another one. Still thinking through combinations and permutations. How many 4 suspect lineups can a police department create if they can choose any of the 15 men currently in the jail? So you have to think about your favorite cop show on TV, where they bring the guys out and put them in front of the big thing that has all the heights, and the victim is behind a glass window, and he or she is looking at the list of these guys, all these guys standing up there, and trying to pick out the right one. Let's see if this works. Are we selecting our objects out of a set of n? I think we are. We've got the 15 men in the jail, and we're picking 4 out of 15. That's promising. Objects are chosen without repetition. No object is used more than once. Could you put Guido on the left end and then later on pick Guido again and have him somewhere else? That's not going to work. You're not going to pick Guido twice. So you cannot have repetition. That means we are looking at either one of these formulas. We're going to be okay to use either one. Which one? Is the order important? Is the order not important? The question says, how many lineups can the police department have? Now, if Guido is on the left or Guido is on the right, you still have Guido, but is the lineup the same or different? I believe if we think about this one, we're thinking about arrangements. How the men are arranged makes a different lineup. Now, Is that immediately 100% obvious? We're kind of having to use some of our own intuition here. But it would be a different appearance, a different arrangement if I had the same four guys, but Guido was on the left or Guido was on the right. So I believe we're looking at the word arrangement. And I think if you can look at a problem and sense a feeling of arrangement going on, then I think you may indeed have the idea of a permutation. This is a permutation. We're choosing 4 out of 15. So it'd be 15p4. Doing that on the calculator, 15, math, probability, NPR, 4. 15p4 is 32,760 different arrangements. Hope that helps. I've got 2 more examples that I want to work for you that are a little bit different because you're essentially going to be looking at picking 2 sets. Let me show you what I mean by that. So a Senate committee consists of 6 Republicans and 5 Democrats. How many different subcommittees can you create from that committee that consist of 3 Republicans and 2 Democrats? How is this different from other problems? What's different here is you're no longer interested in just picking any 5 people. You specifically want 3 of them to come from the set of Republicans and 2 of them to come from the set of Democrats. It's really 2 separate choices because you want to specify from where the people are chosen. We'll have to figure out how to deal with that in a minute. But before we go any farther, let's just see whether one of these formulas might be useful to us. Are we picking a smaller number of objects out of a larger number of objects? Yep, that's good. We are picking a smaller number out of a larger number. Are objects chosen without repetition? Would you choose the same senator twice? No, you would not have any repetition. Do you care about how they are arranged? Is the order important? Or is it just the set of senators that you have and you don't really care about the order? You can arrange them around the table any way you want. I think this is talking about subsets, much like the committee question we had a while back. Now, how do we indicate that we've got really 2 selections going on? We are going to pick 2 of the 6 Republicans. That's going to be 6C2. And we're going to pick, we're picking 3 Republicans, 6C3, 3 out of the 6 Republicans. And we're picking 2 of the 5 Democrats, 5C2. How do we put that together? Well, what is the basic principle that underlies everything else in counting? It's the multiplication principle. So if you think about this as first choosing the Republicans and then choosing the Democrat, select that sequence of choices, you would multiply the 2 together. 6C3, picking 3 out of 6 Republicans, 5C2, picking 2 out of 5 Democrats, making those choices separately, multiplying the numbers together because the most fundamental principle is the fundamental accounting principle. I've written this out, but how do we do this on our calculator? The calculator can do this all at one time. Just start with 6, roll over to probability, down to combinations, enter the 3. Now don't hit enter yet, instead hit multiply. And then, actually I think we need to, let me use the arrow to make sure I'm no longer in the subscript. Notice that I'm in the subscript right now, which would mean I'd be changing that second number. Use the right arrow to get out of the subscript, then hit the multiply. and then 5 math, probability, NCR, 2, enter 200 possible subcommittees. Hope that makes sense. My last example that I want to work for you is going to resemble the question about the cards that we had a little while ago. But again, I'm going to be more specific about where I want the card to come from. How many 5-card hands have 3 aces and 2 kings? So I'm not just picking any 5 cards out of all possible cards. I specifically want to choose 3 of the aces and 2 of the kings. Let's go down the checklist. Are we selecting our objects out of N? You bet. Is our objects chosen without repetition? Could you pick the same card twice? Not if you don't have someone cheating you. So good there. Do you care about the order? Are you interested in how the cards are arranged? I don't think so. You're only interested in the set of cards you have. So we're going to be using a combination formula, but we are specifically saying that we want to pick 3 aces and 2 kings. When you have questions that involve cards, unfortunately, you do have to know what a deck of cards looks like, and there are pictures that you can find online if it's not terribly familiar with you, to you. But in any deck of cards, there are 4 aces, and there are also 4 kings. So what you're wanting to do is you're wanting to pick 3 of the 4 aces and 2 of the 4 kings, 4C3 times 4C2. Let's do that, and this will be our final example. So 4 math, probability, C isn't, you can just do this in your sleep now, NCR, 3, get out of the subscript by using the arrow, times, and then 4 math, probability, NCR, 2, 4C3 times 4C2, the number of hands that would consist of 3 aces and 2 kings is 24. Last observation here, you might wonder, the number 5 is mentioned here. Where does the 5 show up in the calculation? Well, not really anywhere. We are wanting to be more specific about where those 5 cards are coming from. Some of them are coming from the aces, some from the kings. It's the numbers 3 and 2 that are relevant here. The number 5 is actually not used anywhere in this calculation. Well, anyway, that's a number of examples of counting problems looking at the fundamental counting principle, permutations and combinations, and talking through, I hope, an orderly way that you can decide whether you can use one of the 2 formulas. And then once you've decided whether you can, which one you choose. And finally, how to actually do those calculations with whatever technology you might have available. So I hope this has been very useful to you, and best of luck on your homework.